In the 1990s, the renowned physicist Marlan Scully from Texas A&M University suggested an experiment that demonstrated on the lab bench that one could change the past from the present. The experiment has been repeated many times since then, and is considered a prime example of a so-called delayed choice experiment. This astonishing experiment will be demonstrated here in a simplified form.
Yes, let's take a look at what's set up here. This is the well-known Scully experiment, albeit in a simplified form. We want to demonstrate what exactly is being measured and what we actually see. It's important to understand that a particle can behave like a wave or like a particle. So, the famous question is, what is light? And ultimately, what is matter? This question has always preoccupied physicists. For example, there was a debate about whether light is a particle or consists of waves. Experiments like diffraction or passing light through a prism, which are typically only possible with waves, have been problematic. On the other hand, Einstein received the Nobel Prize for an effect he called the photoelectric effect, which posits that light has particle-like properties. This is because it's the only way to explain how, for example, electrons can be ejected from selenium, as is done in your rooftop photovoltaic system, to generate electricity. This requires a lot of energy, which small particles possess, but waves do not. Yes, this is essentially how the so-called dualism was born. The question arose of what is light really? Is it a wave or a particle? The answer, if we were to answer it today, would be it is neither. This applies not only to light but to all matter. We are all made up of atoms, and atoms in turn consist of the atomic nucleus, electrons, and so on, all tiny particles. And this applies to these tiny particles just as it does to light. They have the same properties in this area. Yes, the question arose of what is light really? Is it a wave or a particle? The moment you observe it, this Schrödingerian wave solution collapses and the particle localizes to some fixed point. Then the very property you want to observe, namely what the particle looks like without actually observing it, is destroyed. Yes, there has been a lot of thought given to what could be done, but ultimately it hasn't been possible to explicitly observe a quantum system. But it can be described mathematically. This allows us to calculate properties that this quantum system possesses and that are also utilized, as Scully did in his experiment. But ultimately it seems that matter and light are something else entirely, and depending on the apparatus used to measure them, this quantum system behaves either as a wave, for example, when you magnify light with a magnifying glass, or it sometimes behaves as a particle when you want to generate electricity. Yes, so the problem is that there is wave behavior and there is particle behavior. Wave behavior also leads to the well-known phenomenon of interference. You know that when you send light through a piece of metal with two slits in it, a pattern of light and dark stripes appears behind it. This can be explained as follows. If a water wave were to approach these slits, two smaller water waves would form behind them. These waves would overlap in such a way that some wave crests add up, while others fall into troughs and cancel each other out. When they cancel each other out, these are the dark areas. When they overlap, these are the bright areas. And there's nothing in between. Yes, that's wave behavior. If you were to spray particles, like a jet of sand, onto the two slits, you wouldn't get this phenomenon. Then there are no interference fringes. There's simply a blob, a patch with the sand particles on it, behind the slits. Whether or not you get interference depends on the size of the slit relative to the size of material being sent through it. This means the size of the slit relative to the bigness of material being sent through it. So, if the slits are small enough and the particles are small enough, then I get this interference pattern, which corresponds to wave behavior. Okay, and what does all this have to do with us? Well, let's imagine here, on this lab bench, there's a crystal, and in front of it is a device that generates a beam of light, for example, laser light. You can even do it like this. There are photon guns that shoot individual photons at this crystal. One particle every second, for example. You can slow this down and reduce it so much that you can get down to individual photons. Yes, and if you send such a photon at a specific crystal, then, just like with waves, the crystal splits this single particle into two particles, specifically two particles of lower intensity. If we talk about waves again, it would be like a wave splitting into two smaller waves that fly apart in different directions. Now these two particles, these two smaller photons, are called twin photons because they have a property that larger particles don't have. They are entangled. Entanglement is essentially the fact that two particles can interact with each other and are indistinguishable. Interaction means that if you change something about one particle, something about the other changes instantly. For example, if you observe one of the particles, then some physical property of the other particle changes simultaneously without any time delay, no matter where in the universe this happens. Marlan aspect conducted experiments on this timeless interaction of particles, so this is experimentally proven. And now we have two such entangled particles. Entanglement is a kind of love affair. They were once one single entity, meaning the two were once just one photon that entered the crystal. These two particles are still so enamored with each other that they have a kind of agreement which says, if at all possible, we want to reunite, no matter how or where. Well, this reunification takes place here on the lab bench. So, when these two particles emerge from the crystal in different directions, you can see that two mirrors are set up here that reflect these two particles in such a way that they meet again at a specific point. And at this point where they meet again, we now place a semi-transparent mirror. You're familiar with semi-transparent mirrors. You know them from sunglasses, where you see your reflection when you stand in front of them. But it's clear that it's only semi-transparent, otherwise someone looking through it from the inside wouldn't be able to see anything. So not all the light is reflected like in a real mirror, some of it passes through. These mirrors can be adjusted in a way that half the light passes through and the other half is reflected. You can imagine it a bit like having two ping-pong balls that are reflected by the mirrors and hit a perforated wall. The holes are sized and arranged so that half of the ping-pong balls that hit the whole pattern happen to fall into one hole, meaning they pass through, while the other half are reflected between two holes. If you imagine it like this, there are four possible scenarios. We have two incoming particles, one from the right and one from the left. And now we have the four scenarios. The right particle can be reflected and the left one can be reflected. Or they can both pass through a hole. Or one particle can be reflected and the other pass through the hole and vice versa. So we have four possible cases, and if you were to actually use ping-pong balls and a hole pattern, that's exactly what would happen. At the back are two detectors, one for the right side and one for the left where the particle arrives. So if you have a 50% hole pattern, you would get each of the four cases with a 25% probability. So if you send 100 balls through, on average you'll get 25 that are reflected to the right and left, 25 that go through both holes, 25 where one is reflected and the other passes through, and another 25 vice versa. Those would be the classic cases, but it's not like that with photons or electrons, because with very small particles this duality applies. And because of this wave-like property, as long as we don't observe these things, the particles do the following through their love agreement. The particles behave at this semi-transparent mirror in such a way that they subsequently merge, becoming one again, so to speak. Yes, that means there aren't four cases here, but only two, and this is, of course, experimentally verifiable. You can perform the experiment. Interference fringes are created, so to speak. Yes, although the individual particles don't form a stream of particles over time, but are simply two per unit of time, the love agreement ensures that either one particle, for example, the right one, is reflected, in which case the left particle passes through a hole, or vice versa, if the left one is reflected, then the right one passes through a hole. The two other scenarios, that both are reflected and then don't merge, or that both pass through separate holes simultaneously and also don't merge, don't occur in the experiments. That's just how it is. Even the calculations of quantum mechanics predict it so. So none of this is particularly remarkable. That's just how it is. It can be measured, it can be described mathematically. Now why and how and what exactly this love relationship looks like, well, who really knows? But it's an experiment that can be conducted. So Scully became interested in which path each of the two particles took before reuniting, because you can't see it afterward. At the detectors, two particles are always reunited. you can't reconstruct which path each particle took. Well, the idea by Marlan Scully was you simply place a marker in the path of one of the two particles, and this is done with so-called polarization filters. These are filters that rotate the plane of oscillation of light, but otherwise have no influence on the measurement process, but the particle is essentially marked. The analogy with ping-pong balls is as if you put a dab of paint on one of the two balls while it's traveling so that its location is recognizable. Now, the interesting thing is, because of this marker, the love agreement suddenly no longer applies, the wave behavior disappears. These things now behave like ordinary grains of sand or ping-pong balls that you send along. So, if one photon is labeled, then suddenly all four classical cases reappear at the detectors. Then there are not only combined photons again, but there are also separated ones. So there are also none combined cases again, half the cases as before, and the other 2 times 25% are now also present. That's just how it is, and you can't change it. But what's interesting now is this Scully devised the following behind this whole mask, that is, behind this semi-closed mirror. In front of both detectors, he sets up an apparatus, namely a second polarizing filter, which cancels out the polarization effect but does not affect the other, unlabeled photon. That means if a photon was previously labeled by the first polarizing filter, then this label is erased. That's why it's called a quantum eraser, because the marking has been deleted. Yes, if it wasn't marked at all, means it was the other photon that wasn't marked, then nothing happens. Yes, it stays as it is. In a way, it's like a washing machine positioned in front of the detectors, which washes any potential stains out of these ping-pong balls. If there wasn't one, it stays as it was, and if there was one, it's gone afterward. Yes, the clever thing about the whole thing is that I can now move this detector far enough away from the mirror and also position this washing machine, this eraser, so that I can decide whether to turn the eraser on or off after the photons have already passed through the whole mask. That means I decide right before the detectors whether to turn on the washing machine so that any potential stains are erased, or I decide not to turn it on and the stain stays where it is. Yes, the trick is that I can now move this detector far enough away from the mirror and also position this washing machine, this eraser, so that I can decide whether to turn it on or off after the photons have already passed through the semi-transparent mirror. Yes, so I can make this decision at a point in time when the particles have already passed through this whole mask. That's why it's called delayed choice. So I wait to make my choice until the particles have already passed through this semi-transparent mirror. And what happens next is astonishing. If I turn on the washing machine after the particles have already passed through this whole pattern mask, then the reunification agreement takes effect again. That means I get only the 2 wave cases again, so to speak. The reunited cases where the 2 particles are reunited at the detectors. However, if I don't turn on the washing machine, then I have the 4 classic cases, as I said. And the problem now is, how do the 2 particles know when they arrive at this semi-converged mirror that I will later, of my own free will, decide to turn the washing machine on or off? How do they know that? Because that only happens later. They would have to know beforehand at the whole wall how I will decide later. Yes, because the agreement is we always stay together. If you fly through the hole, I will be reflected. If I fly through the hole, you will be reflected. Yes, but this decision of the particles is already made at the mirror. But afterwards, if I then turn on the washing machine, suddenly there are only combined photons again. This means either the photons can see into the future, that they already know at the semi-transparent wall what I intend to do later. Or the interpretation is that my action, namely turning the washing machine on or off, using this quantum eraser or not, influences backwards in time the behavior of the 2 particles at this semi-transparent mirror. That's one possible interpretation. In any case, it's technically feasible. It can be measured. Scully has even devised an experiment where the decision of whether or not to turn on the quantum eraser is made days later, long after the particles have arrived at the detectors. But you must not look at the detectors beforehand, so to speak, because then it's too late, then the decision has already been made. But if I decide afterward, retrospectively, to say, well, I've now switched on the quantum eraser, then the particles arrive exactly where they were measured yesterday or the day before. That's just how it is, one puzzle after another. But it seems possible to effect a change in the past from the present, at least with entangled particles. How far this can be used in practice for time travel or something similar, or for altering one's own past, is another question entirely. You would have to be entangled with your duplicate to change anything. Who knows? In any case, it's something that apparently is what it is, and it's not limited to this little lab bench here. It can even be done on a cosmic scale, because thankfully there are quasars out there, which it seems also to be possible to effect changes in the past from the present. Quasars are stars that emit light in many directions like a candle, and in between lies a large Milky Way galaxy. You couldn't actually observe the quasar itself, but the light is bended around the galaxy. This gravitational lensing, as it's called, is essentially the effect of a large Milky Way galaxy. It acts like a large lens, causing the light rays to travel around the top and bottom. Now on Earth, you can conduct an experiment that replicates this behavior, but in reverse time, so that the light rays around this gravitational lens behave both as waves and as particles. That is, they pass through the top and bottom alternately. And this behavior is even more astonishing because the light rays passed through this galaxy millions of years ago, long before Earth existed. This means that, through an experiment today, I can essentially influence how light traveled across a galaxy millions of years ago. Measurement-wise, this seems to be the case. You could even conduct two experiments simultaneously. One is set up so that the light has to travel around either the top or the bottom, the other so that both happen simultaneously. And then the question arises, what actually happened in the past? Hugh Everett has a solution for this. He says there's a many-walled theory that states that whenever you make a decision, like whether to turn a washing machine on or off, the universe splits, it duplicates itself, but there are different pasts. Yes, for example, there's a past where the two particles merged, and simultaneously there's a parallel universe where the particles didn't merge. And which one you slip into depends on your decision. You essentially always slip into the past that corresponds to your washing machine off situation, but the other worlds are just as real, according to Everett. The whole thing is a bit unsatisfying because it's very speculative, and ultimately, everything they do is affected. If you decide, for example, not to commit a murder, the universe splits, and in another universe you commit that murder. Yes, so it's practically irrelevant how you decide. There's always a universe where you chose differently. This is of course highly speculative and not accepted by many physicists. Yes, this model dates back to the 1950s, but it is an explanation. It's a theoretical model that fits the facts. Now let's briefly draw a conclusion. Why does this raise the question of whether space and time exist? Well, Nobel laureate Alan Aspect experimentally demonstrated that entangled particles behave as if there were no space between them, since they act like a single object. Even if billions of kilometers separate them, they exchange information without any time delay, or rather, they behave as if they were just a single particle. The old assumption that there might be hidden variables connecting the two objects has also been experimentally disproven. Keyword Bell's inequalities. So much for space, now for time. The experiment demonstrated here showed that the particles behave over time as if they were a single object extending from the past into the future. This seems to suggest that the phenomenon of time is merely a perception arising in the observer, but actually possesses no reality. One more comment on the recurring question of whether quantum physics refutes causality. The answer depends on how the definition of the law of causality is chosen. There are several definitions. The most general version is, everything that comes into existence has a cause. Note, not everything that exists has a cause, but only everything that comes into existence has a cause. This law is not violated by quantum physics. If this law is restricted, as is often done in physics, to the principle that identical causes always produce identical effects, then quantum physics clearly violates this law. There appears to be true randomness. Nevertheless, the general version of the law of causality is not violated. For every random event that comes into existence has at least one cause, namely the random generator. However, the effects are not always the same, even with the same cause. But quantum mechanics allows us to specify the set of all possible effects, from which one then arises randomly, along with its probability of occurrence. So what is violated is a temporal constraint on causality. While normally the cause occurs first, followed by the effect, Alan Aspect was able to demonstrate in his experiments that a cause arises absolutely simultaneously with its effect, even across arbitrarily large spatial distances. Our experiment then further demonstrates that a cause can also occur after the effect, such as the switching on and off of the quantum eraser. This is the cause that arises timely spoken after the effect, namely the behavior of the reunification at the semi-transparent mirror. That is, the effect in the past, impressively demonstrated here. Here, then, the cause occurs after the effect. So, with quantum physics, one doesn't have to abandon the law of causality, but only the uniqueness of an effect to the same cause and the temporal sequence of cause and effect. The law of causality thus becomes a meta principle independent of space and time. And what's next at the MIT and the USA entanglement and thus an exchange of information between particles that have already been destroyed, which means they are essentially dead, and particles that don't yet exist, which means they will only be created later, has now been experimentally demonstrated. All of this shows that our conception of space and time probably has little to do with reality out there. Some physicists, therefore, believe that what is out there only comes into being through our observation, a theory that seems to be confirmed by further quantum physics experiments. So, I hope this has given you something to think about, and I thank you for your attention.
Is more than just a game. We'll never be the same. And all the love you gave, I remember and long for more than joy and fame. Just one thing was my aim. It's more than I could claim. It's alive with you. I sing this song for you, for everyone I knew, for times when I felt blue and you stood with me. I cried the time you spent, I wish there was no end to all the things we've done, but life is going on. I thank you, my friends, for all the days you spent when you joined me. Now the curtain has to fall, and I will thank you all. This treasure is not small that I carry in my heart.